Welcome to the Faster Podcast by FLO Cycling, the podcast where we talk about anything and everything that makes you faster on your bike. This is episode 35, and today we have Andrew Buckrell from 4Eyes joining us on the show. During this episode, we'll discuss the virtual wind tunnel technology that Andrew and his team have developed. Listen to this episode to learn how using an iPad and a 3D scanner can help you become a faster cyclist. Hey, this is Chris with FLO. When we're not producing this podcast, our team at FLO is designing some of the fastest carbon fiber bicycle wheels in the world. As a thank you for being a listener of our podcast, Faster by FLO, we wanted to offer you 20% off your next purchase of wheels at flocycling.com. Head over to our website and pick up a set of wheels to make you faster at your next race or ride. Simply use coupon code PODCAST, that's PODCAST, in all uppercase letters when checking out to get 20% off your order. Thanks again for listening to Faster. We hope you enjoy the show. All right, Mr. Andrew Buckrell, welcome to the show. How you doing today?
I'm doing excellent, and thank you very much for having me.
You're very welcome. It's an honor.
You're welcome.
Yeah. So I think we met first because I believe you were a customer first. Is that correct?
Yeah, actually, fairly early on, I think in your business, we had, I had at least purchased your wheels because I thought, hey, this is pretty cool. You're offering something at a good price, and I had a lot of respect for the development and technology you were putting into it. So that was something, and the transparency is something you didn't really see in the market. There were a lot of other manufacturers out there, selling for 2 or 3 times the price, and to be perfectly honest, I just couldn't afford their product. So that drew me towards you, and then I started digging, and it was like, hey, these guys know what they're doing. And a really cool side note is I went to a conference on computational fluid dynamics, and they actually used your iterative design process as kind of a case study or a benchmark for their software platform.
Way. That's cool to hear.
It might be.
Yeah.
That's really cool. And I guess just to clarify, that means a lot coming from you because you have like 48 degrees. How many degrees do you have?
Well, it depends on how you count. I'm partway through a PhD, and I would like to think I'm on the good part where I'm nearly done, but I'm 7 years into the PhD. So
yeah, well, I get it. You're on a business and running things, so that's how it goes. Yeah.
Yeah. It turns out there's not a lot of time left for studying when you're trying to get a business off the ground. But
I hear you.
Yeah, I did my master's in mechanical engineering, and then I actually spent a little bit of time doing some research at, I believe, the university you guys went to at UNB. Is that?
Yeah, we did go there.
In
wow,
Fredericton or
good
St.
reference.
I was in Fredericton.
Oh, yeah.
Spent a lot of time there.
Spent a lot of time there.
Yeah.
Wow, small world.
Did you work with any of the profs there?
Yeah, I can't remember his name right now. It was only a week and a half. I was doing some experimental work there, but it was some experimental imaging in a heat exchanger, which is what my PhD work is based on. But it's all computational work I'm doing. So this was kind of getting the other side of things, the experimental work.
Cool.
Oh, very cool.
All right, well, the focus of this show is going to be the virtual wind tunnel technology that you guys have. But I think, the first time we actually met in person was at Interbike, and you were there starting a company that's was known as Stack, and we'll talk about where that is now. But your background with how that company got started is pretty cool. So can you talk to us a little bit about what your journey was to starting Stack and how that started and what took shape?
So I guess the first disclaimer I would say to anyone is if you're thinking of starting your own business, just be prepared for a lot of stress. So I'm sure you guys probably know this, and I know we've had some discussions on the side in the past, and we've gone through some of the similar hurdles, but there's just so much that goes on when you start it. And this is part of the reason my PhD is not done, is just there's an unexpected amount of work that comes along with it. But the actual motivation came from, I was at a theme park, so Canada's Wonderland near Toronto, and I was watching...
Great place.
Yep.
Yeah, I spent a lot of time there and felt quite sick there as well. So
there's a few rides that'll do that to you.
Oh, yeah. And I found it's, you feel worse as you get older. So there's a lot of things that go wrong when you get older.
Yes.
But the motivation for the trainer itself came from watching the drop zone ride. So they use a magnetic braking system, which is completely non-contact, and it relies on eddy current generation to actually slow down this, multiple 1,000-kilogram mechanism from like 100 kilometers an hour basically down to zero. And I thought, this is cool. This is really neat because it's no contact. It doesn't have any wearing parts. It doesn't really make any noise, and it's really effective.
Wow.
So I kind of got thinking about this, and I went home and talked to a friend of mine who ended up being one of the co-founders, Art Hare, and we got just basically talking and saying, what can we use this for? And initially I was thinking, what if we can make a more aerodynamic brake that can really be hidden inside a fork or something like that? And then that was, after some experimentation, we found, that doesn't really work that well. But if we put the magnets near an alloy rim, with enough magnets, you can actually dissipate a lot of energy. So as a result, we've got this trainer, which now doesn't touch the wheel at all. And it's able to generate, 1,000 watts of resistance, 2,000 watts of resistance if you can spin the wheel fast enough. We ended up with this trainer that was super compact and portable, lightweight, and had a ton of resistance and didn't wear down your tire at all. So you didn't even really need a tire. You could run without a training tire or with your race tire. It didn't make any noise. So it solved two of the big problems that were associated with trainers at the time. And I think this was back in about 2015.
Yep.
So things have come a long way since then, but we still had a really unique technology offering that allowed us to kind of at least erode some of the market share of kind of the big players like Tax and Wahoo and Kinetic and Ceres.
Very cool. And then
Right.
that originally was just you set your resistance, right? And then eventually you guys developed a smart version of it that is very similar to a Kicker or a Tax Neo Smart, right? Where it's an erg and it automatically adjusts the resistance based on a training program like Trainer Road or Zwift, right?
Yeah, exactly. So the very first iteration was just completely dumb, where not dumb in terms of its technology, but a dumb trainer. But there was no electronics. It was purely mechanical. So you would set the magnets, and we had these wheel weights to kind of simulate the road feel. And I'll get back to those in a second. But the magnets would be self-set, and then you just ride. And the faster you ride, kind of like a fluid trainer, the more energy is dissipated. We made a small modification to that and added a load cell at the mounting point for the magnets. Yep. And that was able to measure wheel speed and power. And because of how we're actually measuring the reaction force through the load cell, it's a very, very easy and accurate calculation of power, because it's essentially just a tangential force. So there's no weird components that we're trying to remove. Like for a crank-based power meter, you're getting off-axis forces that you're trying to remove and isolate from the signal. But for us, it was just purely strain, tangential strain. So it was super easy to get an accurate power. So we sold those for, I think, 1.5 or 2 years. And we were always getting these questions like, when are you coming out with a smart trainer? So we eventually did. And we had the magnets adjusted by a control system that would look for basically what's your target power. And then it would adjust it based on a bit of a feedback loop. So this was kind of where the line between Stack and where we are now at Four Eyes, that line was kind of drawn at this point. So the development of the trainer, it always continued in the background. But after the Halcyon, which was the smart version, we came over to Four Eyes. And so through that acquisition, which was really interesting process on its own, but one of the mandates for us coming over was, okay, we need to figure out how to make this at a much lower cost so that we can pass those savings along to the consumers and have like a very price effective smart trainer. And how do we get rid of the wheel weights? Because honestly, it was such a pain. We got better at them, but the customers still hated them. And it was the biggest holdup with the design is getting these wheel weights so you get a proper road feel. So the development that's happened over the summer, it's been really interesting because we've been essentially faking inertia. So what the effect of inertia is with a trainer is basically smoothing out wheel speed variations in your pedal stroke.
Yep.
So if you can minimize those wheel speed variations, you can make it feel like you've got a really heavy wheel. And what we do is a very high resolution of your measurement of your wheel speed. And this is using your spokes as an encoder. So we get this very accurate signal. We can detect changes in wheel speed, and then we basically predict what the rider is going to need, and then we move the magnets to that position to mimic the effects of just having inertia. So throughout your pedal stroke, you can see the magnets moving in and out. And I won't even claim to be involved in the software development. So that was Art Hare, who's just absolutely brilliant. And he's come up with a really cool algorithm for predicting rider torque and wheel speed variation. So it's been...
Yeah, he's like a mad scientist. I've met him several times. You guys are actually up here one time in Las Vegas, and you came in to borrow some bikes and stuff to go out for a ride out in Red Rock.
That's right, yeah.
Yeah, no, I remember he was out here. He's a smart fella. I will give him that.
Oh, yeah, a ton of respect for him. And the other thing is he works just by necessity. There wasn't anyone else who could do software in our company, but he was working basically in isolation. So he didn't have anyone to check over his work or to confirm things. I was just there to bounce ideas. And I would occasionally stumble on something that might give him another idea, but really that was my only involvement in the software design. But it's super cool what he's achieved.
That is so cool. All right. One more thing I want to talk about quickly. We don't have to get into crazy detail, but selling your business, I mean, for every entrepreneur is maybe a dream. So you guys were acquired by 4 Eyes. Is there anything that you can tell about that story or share that would be cool or interesting?
Well, I think it was... we had encountered each other at the right time and the right place. So we met through a mutual sponsorship of Cycling Canada. And it was one of their retreats that the CEO of 4 Eyes, Kip Fife, and I got talking, and we found we had a lot in common. And I would say, even though it's kind of structured as an acquisition, it was almost like a job interview where we realized we have so much in common with the way we think and the way we approach problems that it made sense for us to be working together. And that's really how it evolved. So the intent was never like a purchase and a cut and release where they get the technology and then we disappear with a golden parachute or something. The intent was always to get us under their umbrella and to help just further the entire company vision. So working together instead of working at separate ends of the country and just trying to not really compete, but just working in isolation of each other. So it's really combined resources and sharing. But that's the engineer's viewpoint. When you get to the financial and the legal side of things, there's so many things to do. So,
Yeah. I can only imagine. Yeah, cool. All right, well, let's get into the virtual wind tunnel because that's what I want this show to be primarily about, because this show is about getting faster on your bike, and training obviously helps with that. But the wind tunnel is really cool and is a direct correlation to your speed. So your virtual wind tunnel, the entire process starts with a 3D scan. So can you talk about how that is done and what equipment is needed to do the virtual scan?
So the equipment needed is actually, the whole focus of this was to have something that's actually an effective or like a cost-effective replacement for a wind tunnel, because you guys have spent time in the wind tunnel, and I'm sure your wallets can attest to the pain of that.
Yeah, they're cheap.
Yeah. So if you're looking for a nice breeze, the cheapest way is definitely to go sit in a wind tunnel for a few hours.
Yeah.
But no, you're looking at like $500 to $1,000 an hour plus setup and teardown time, and they don't care if you're running the wind tunnel or not. Like you're paying regardless of what's happening inside.
Yeah, it rivals Bora Bora for a breeze. So yeah.
So the whole concept was, how can we do this numerically using existing technology that's cost effective for the end user, really democratizing the field of aerodynamics. So we started off with using the Microsoft Kinect, which was kind of, at the time we were starting to develop this, people were just starting to kind of hack it, and Microsoft had released an SDK that would allow you to develop. So Art, when he wasn't busy programming trainer stuff, he was helping develop some software tools that could use the Kinect to essentially record a data stream that had depth. So it's like recording a depth movie. And we would reconstruct it into a 3D model after the fact. So you basically, initially you would carry around a Kinect, just wave it in front of a rider for a minute or two, and then you would capture the depth data that could be turned into this fairly high resolution 3D model. And the great thing about the Kinect and the technology in there was that it's based on a chipset that costs like $150 or less. So it wasn't in line with these commercial 3D scanners that are like $5,000 to $10,000 to $30,000 to $50,000. And really the sky's the limit for those. But we wanted something that was reasonable to use. Instead of having to either have one person with an expensive scanner traveling the world, we wanted something that could be accessible to everyone. So after a year or two of development and understanding kind of what's going on, we we found out about this other sensor technology that was built on the same chipset that the Kinect provided. And this was the structure sensor. So Occipital is the company that developed it. And I think they bought the technology from Microsoft. And Apple has since purchased some of the chipset from either from them or from Microsoft. Or it's kind of a convoluted path. But yeah, we ended up with the structure scanner, which is just a little iPad attachment that costs between $300 and $400 US. And you toss it on an iPad, and basically you just record a movie. And you send the data to us. We'll process it. We do a CFD analysis and then spit out some results. And in the past year or so, the thing I'm most proud of is that we've been able to now modify your bike position digitally. So if you say, I want to increase my stack height or reduce my stack height or change my helmet or change my fit slightly, we can actually do that digitally. So you send us one scan, and after the fact, we can go in and make all these changes, which means it's very time efficient, it's very cost effective, and it delivers results that are more or less on par with wind tunnels.
Wow, that's really cool.
Wow. The second thing about the sensors, how much do one of these sensors generally cost?
So $399 is kind of the standard that they have for pricing. I think at the time of recording now, they're releasing a second generation of the sensor, which is supposed to be higher resolution, but at the moment they're having some kind of hardware issue internally, so they've kind of frozen some of the access we have to development. So you can't purchase the first generation sensor. The second generation, the hardware is out there, but the firmware that allows you to access all the benefits isn't quite there. So it's in that price range. But the really cool thing that we don't have working yet, but we're looking at, is the iPhone is using the same chipset now. So so basically, if you have one of the iPhone X or the iPhone 11s, you now have access to a 3D scanner. So I was talking about democratizing. The True Depth scanner, so what they use for facial recognition. There's a handful of apps that you can kind of see, but nothing that useful yet. But if we can now record the data using that scanner, the barrier to entry for people is basically zero. So you don't even have to pay if you know someone who has an iPhone, minus $1,000 or so.
Number one, on the iPhone, is the sensor embedded only in the front-facing camera, or is it in the back cameras as well?
It's only in the front. So
it's in the front-facing camera.
Mm-hmm.
Okay, that's cool. And then, so if we look at the resolution from, let's say, Gen 1 of the scanner versus Gen 2 and then the iPhone, how does that resolution compare across those three devices?
Well, I think I don't know the exact numbers for just the pixel resolution, but the depth resolution is within 0.5 millimeter. I think if you're at close range, if you go to far range, like if you're looking across the room, then the resolution might be 5 centimeters. So it's nonlinear, and it goes up with distance. So if you hold it in close, it's like when you're trying to squint to see small print, right? You can see it better when you're holding it close, obviously. Same thing with the scanner. So if you hold it kind of at an optimal distance, you can get quite good resolution out of the 3D scanner, enough that you can pick up folds in clothing and textures and things like that, but not enough that you can pick up like maybe, for example, looking at my hand, like just the folds in the skin. It won't pick up that level of resolution. And to be honest, and I think some of your questions are based around this, but to be honest, like at some point there's diminishing returns with computational fluid dynamics in terms of what kind of resolution you provide.
Okay. All right. So when you process a shape, is it just the static shape or is it a dynamic shape that moves? So I'm thinking when the rider pedals or, his legs are moving, the chain is moving, the derailleur's spinning, are you capturing a static position or a dynamic position or movement?
We are capturing static at the moment. We're doing experiments to basically use motion capture data to animate. So using the same technology we use to adjust the bike fit, we're trying to animate a rider based on motion capture data. The issue is when you get to unsteady simulations, you're looking at 10 to 100 times the computational cost for maybe 0.5 to 1% increase in accuracy. So this is well within diminishing returns. Like it's a cool academic thing, but I would argue it's not really relevant. And we have good correlation for where your pedals are versus your average drag. That it's not 100% accurate for every rider, but across the board, it's fairly accurate.
Okay, so my next question was, how do you account for the motion? But you're saying the difference between a rider moving versus a static image is 1% or 2%?
Well, in terms of the additional information that you capture, so there's actually quite a large variation in the drag for a cyclist over the pedal stroke. So if you go from a vertical crank to a horizontal crank, there's almost a 10% reduction or change in drag. So when you see like Tour de France riders descending, they'll actually have their crank horizontal because that's the lowest drag position. But when you have one leg bent fully and then the other extended, cylinders are not very aerodynamically efficient shapes. So You've got this giant fat leg, or at least in my case, a giant fat leg that's that's extended and creating a ton of drag. So we actually use that position as our baseline, and then we know how that generally relates. And like I said, it's not 100% accurate for every rider, but this is like our main goal is, again, democratizing aerodynamics. So maybe it's not quite at the laboratory level of repeatability, but I think we can talk about this in a bit, but I think there are a lot of arguments to show that we have easily, we've achieved the kind of resolution that you need in order to improve what you're looking after for your position.
Yeah, and I guess let's say you have your leg in the straight, one leg is down and one leg is up, and that's your fixed position. Most of the changes that you're going to make are going to be at the arrow bars, right? So you're going to raise stack, lower stack, move the arms in, move the arms out. So unless you're really changing saddle height, which most people aren't going to change more than maybe a centimeter or two, you're not going to have much change of what's going on at your legs. So the big changes that you're making are the upper body, and that's what you're really focusing on?
Exactly, yeah. There are some minor interactions that can occur. So if you create a low pressure zone behind your extended leg, you might pull the air down your back a little bit more efficiently. So there's some trade-offs here and there, but in general, you're right. Like there's not a ton of stuff that's overlapping in terms of what's happening up front and what happens, in your lower body.
Interesting. Okay. So after somebody takes a scan, I guess the data is just uploaded to Stack. Is that how it works?
Yeah. So we've got, typically we'll organize something with a fitter or a partner that we have, and they'll upload the data to us. And currently we use Dropbox just because it's an easy way of transferring data. We'll process it. We'll develop a model, and you can give me some information for basically what kind of components you're using, things like that. And then what changes you'd like to see in your bike fit. We'll apply those changes, and then we return a report that has some details on like your CDA overall, and it'll have estimated time savings based on your change in CDA and wattage output, and then wattage savings and estimated speed, things like that. So it's kind of useful, actionable data. So knowing if I tuck my head down, I can save 10 watts, for example, and that encourages people to focus on things like that, because it's really easy in an Ironman race to forget about it partway through, because your mind starts to wander and it's generally uncomfortable. And having that in mind and thinking, man, I'm sacrificing 10 watts. Like I could be doing 10 watts less, for example, if my head's down and just having an easier day, or I could be going that much faster. So it helps drive the point home, like how much of an effect aerodynamics has on people.
That's funny. 8 to 10 hours into any race, you really don't care what is happening as long as you're moving forward. So, okay. So you guys get the data, you do an analysis. So what software are you using to do the fluid dynamics analysis?
The software package we're using is called OpenFoam. And it's an open source CFD software. So the barrier to entry for this is just that it's almost impossible to use unless you have some formal training. Unfortunately, I was able to go to a conference a while back and learn how to use it. But the real advantage to using the software is it's extremely scriptable. So you can do the same rider simulation very easily. Over and over again. And it's also, I would argue, one of the most validated CFD codes out there, because the whole open source nature of it means that academics are using it all the time for different studies. So there have been countless studies on the accuracy of the models, the accuracy of the meshing, things like that. So I think as long as you have the ability to use this software, it's one of the best solutions. But it's just not time efficient if you're dealing with a lot of complex problems that are varied. But that's not what we're doing. We're dealing with the same simulation over and over again.
Okay.
Yeah. So when basically the way that it works is somebody scans and then they upload the data and then you guys process it. So how long does it take you to process, let's say, one position?
So one position, like the reconstruction's actually, for me, the most time consuming and labor intensive part. And after that happens, the meshing, so to generate the computational mesh, which is for anyone who doesn't or isn't really aware of CFD, you're basically solving conservation of momentum and pressure, or not conservation of pressure, but conservation of momentum and continuities, the conservation of mass equations. And you're solving it in basically like Lego blocks. So, and these Lego blocks are placed around the model. And it's not just a few, it's like several million. So
cells.
Yeah, so these computational cells. So the mesh takes about 40 minutes to generate. And after that, we do an unsteady simulation. So it actually captures like vortex shedding and some of the dynamics of flow that happen not in a steady nature. Even though our model isn't moving, like the rider isn't moving, the flow around them is not stationary. So we can get some of the more complex interactions that occur. But this simulation takes 3 to 6 hours, depending on how many CPUs we throw at it. And we do it all with cloud computing. So we've got essentially infinite scalability with it.
Oh, I was going to ask you how you're doing that, because you're doing it on like a standard computer. It really depends on your cores. But if you're doing it in the cloud, then that makes some sense for sure.
Yeah.
Cool. How much does it cost you each time you're uploading the data to like process one model? I'm assuming with you're in the cloud, you get a pretty low run rate.
Yeah, like it doesn't cost that much in computational costs, which is really encouraging for the future. But really, the labor is where it's expensive. Like just in general, people are expensive.
So the cost to the customer though would be what?
Though,
yeah. The customer cost. Again, we let our partners dictate this a little bit, but in general, depending on how many positions that you want analyzed, you could be looking at $100 to $200 for having 5 to 6 positions compared.
Oh, okay. Wow, that's pretty cool. Okay, so and what parameters do you use when processing the data? Are you using wind speed, yaw angles? What are you guys doing? What are you throwing at it?
And again, this depends somewhat on the requirements of the customer, but we've done, well, generally speaking, we do the same wind speed for everything. So when you get into aerodynamics, there's a whole bunch of non-dimensional numbers. And basically, once you get above a certain point, so with the Reynolds number, if it becomes large enough, then you can assume everything that's faster than that, basically the same thing happens. And we're kind of on the good side of that, where everything starts becoming self-similar. So we test at around 45 kilometers an hour, which is a little bit high for some people, but it gets us into that range where there's not a huge change in the performance. And for yaw angle, typically we just analyze 0 degrees. It's easily possible to do multiple yaw angles for each rider position that we're looking at. And I agree that there would be more actionable data that could be taken out of that, but it becomes less cost effective, where the computational costs start to become pretty significant and would drive up our final price point. So we want to keep it kind of the most usable, most practical information that most people can take from it. And that's not to say we won't change things in the future, but that's just the way things currently sit.
Yeah, and that's kind of brings up a good point, actually. It's like you go to a wind tunnel and people say, hey, why does everybody run wind tunnel studies at 30 miles per hour or roughly 45 kilometers per hour? It's, you have to create some type of steady enough flow. I mean, that's considered a low speed wind tunnel to actually be able to measure the results that you're looking for. So that makes sense why you guys are doing it in software that way as well. Once the data is processed, you guys are going to send the athlete a report. So what does that report include for the athlete?
So the final report, I'd mentioned a few of these things where we have like the expected speed based on wattage. We have the time savings versus your baseline, the wattage savings versus your baseline. So those kind of things we provide, all the CDA, the raw CDA values. And I would argue those are the most important. Like the other things are, they're useful for someone to look at and say, hey, I can save 5 minutes over an Ironman. And that's great. But if you start to use other tools like Best Bike Split, this is where the power is really unlocked, where now you have a CDA and especially in this case, we've done a bit of work with Ryan Cooper at Best Bike Split, and one of the athletes who works at Training Peaks, and we came up with this really cool result where, using a combination of Best Bike Split and the virtual wind tunnel, we were able to predict his time to within like a few seconds at a 45-minute time trial event. So that was super cool, taking the raw wind speed data and the raw power file, and it was like basically proof that the mathematics work out, which is super cool to see. So,
a couple of seconds?
Yeah, I can send over the link for that afterwards, and then you can post up in the show notes.
We'll put that in the show notes. That's pretty cool.
So that was awesome, because it wasn't like this guess and check where we just kept tweaking and tuning. It was completely blind input from my part, and it was honestly, I think, a bit of a test or proof of concept for Ryan to see how accurate the results would be. And both of us were surprised to see it come that close, because when you're dealing with numerical models, like sometimes, well, there's so many variables that you never expect to be that close. So it was pretty cool to see that.
Wow. Okay.
Smart guy. He's been on the show. He's an interesting guy to talk to for sure.
Oh, yeah. So you said that you manipulate the model to give riders a few position suggestions. How are you actually doing that in the software? How do you move somebody's arm digitally?
So computer animation is really where the thanks belong, because they've developed a lot of these models that, if done properly, will accurately reflect movements of a person. Because if you have a computer animated movie, and people's arms are moving in unrealistic ways, there's going to be a lot of unhappy people, or at least unhappy customers. So they've spent a ton of time and money, and to be honest, movies probably have bigger budgets than most sports-related efforts. So they put a lot of money into the development of these tools and the perfection of these tools, and we're using just a small portion of it, but it's a very useful portion that allows us to manipulate the motions of a rider quite accurately.
Okay, and when you're changing the position, is that something that you're doing manually, or is the software smart enough to kind of self-optimize the position?
At the moment, it's done manually. However, we have a lot of plans for automating the entire process. Okay. So the ideal circumstance that we see in the future, and I think what a lot of customers would love to see, is where you can take a scan, have everything completed, and results returned to you within like an hour or two. That's what people want, just that immediate gratification. And we're not there yet, but there are some things that could be done that are fairly straightforward. Like if we have checkboxes in the app where you say, I want to move my arms by 2 centimeters, or I want to change this by 1 centimeter. And then all of those, once we know what needs to be done, that can be applied to the mesh quite easily. Okay. So
see,
it
that's
could be
interesting, because when we first started, the general industry trend was to make 20, 30, 40, 50 different molds, take them to a wind tunnel and see which one worked. And, when we first started, our budget was nowhere near what it was, now. And we kind of took some ideas and tried a few shapes, and that's what we did. But then we realized that you could automate this, and we've basically moved to a fully automated process where we give an algorithm a list of parameters, and we can test hundreds and hundreds of rim shapes to optimize for exactly the design criteria that we want. And that changed our design, our aerodynamic results drastically just by doing that. So I think if you guys can get to that point, that's going to be a big win for you.
And do you see it? Go ahead.
Oh, I was just going to say that that kind of optimization is really the strength of numerical methods, where you can get in and tweak different variables and you just hammer through it, because computational time is relatively cheap compared to human time.
Yes.
And cloud computing is just unlimited, basically. So the final goal might not actually be to have this input from people. Like, it's always nice to know what's, if I make these changes, what happens. But really, like, what is my optimal position would be the
and you have to be smart enough to know what to give the computer. Like, you can't just say, computer, give me something fast. Right? You have to know, like, this parameter must be met and that parameter must be met. So that's where you come in, obviously, in the design side of whatever you're doing.
Yeah, and I think there's a lot of AI development that would have to happen for that. So, for example, if someone's flexible or not flexible, you need to know how to apply that to the model. So,
yeah. Well, and it would be cool too, like if you guys were able to automate everything on your own end, so you're not having to do it. It's just that would be a really quick turnaround. That'd be super cool.
Yep, and that is the long-term goal. That's what we're marching towards.
Cool.
Nice. Have you guys tested your results against results from a wind tunnel?
So a couple of years ago, I went to the faster wind tunnel with Bentham. So we had scanned a bunch of their athletes, and we've mostly worked with Cody Beals since then, but a lot of our results came within, I think, 2% of their wind tunnel results. And to be honest, you guys have spent a ton of time in the wind tunnel. It's hard to get even that kind of repeatability with the same setup, torn down and set up multiple times. Yeah. So I think we're within the realm of accuracy that you can expect from any method. There's always going to be pros and cons of wind tunnel versus numerical versus outdoor testing. And really, my opinion is that all of them, if available, should be used in conjunction with an unlimited budget and unlimited time. But I think that we're within any reasonable amount of accuracy that can be attributed to any of the methods.
And so do you believe, I mean, what's your belief? I mean, it kind of opens up an interesting topic. You talk about outdoor testing, you talk about wind tunnel, you talk about virtual. You say they should be used together. So what's your belief on how those merge together? And do you eventually see virtual, like your virtual system being able to take over even from a consumer side, but maybe even on a manufacturer side? Like, so I came to you and said, hey, we're looking at developing a new product and we want to see what that, it's been manufactured. Now we want to scan it, and see how that works. What are your thoughts on that?
Well, it can certainly be applied with, if we have an existing model of a cyclist and the manufacturer has CAD data, then that becomes very easy to apply. And that's typically how numerical testing is done, taking the exact CAD data. But when you look at other industries as a model, aviation, for example, like basically unlimited budgets, as far as we're concerned anyway, they spend hundreds of millions of dollars on development, and they'll do this test cycle where they do all of their iterations numerically, and then they validate in the wind tunnel, and then they go back and do more iterations numerically. And it's just, the wind tunnel is kind of minimized because it's just so expensive, especially when you get to like a full-scale aircraft wind tunnel. And that's typically how the industry works, and Formula One follows the same model. And I think it's only a matter of time before cycling fully embraces that. And a lot of companies are using numerical methods right now. And there's no reason that you as a rider can't use the same methodology where you go out and you basically validate your results using either, if it's a still day, your power and your like the drag, you can figure out your speed based on the drag. So there are lots of ways to do it. Like coast down testing is another way of doing it. There's also Aerolabs, Nodeo Connect, things like that you can use. And there's all these different methods that are kind of coming in together. And a lot of people see them as, a one or an either or solution as opposed to working together. But I really want to see it as working together because that's the best way to improve yourself.
I like that.
That's really cool. It's funny you say that because that's kind of been the approach that we've taken. Well, it has been the approach we've taken for the last 4 or 5 years is do everything that we can numerically and then use the wind tunnel to confirm. And it's worked really, really well for us. So as a cost saving measure, it does make a ton of sense. You talked a little bit earlier about how you can manipulate the yaw angle, but it's time consuming. So for manufacturers who are looking for a deeper level of detail, that is something that you can do if needed, right?
Oh, absolutely. And it's not even really that expensive. It's just if you want to do 5 simulations and there's a fixed cost, we could either do 5 yaw angles with the same model or 5 different positions. So it just becomes, if now we're trying to do 5 different positions with 5 yaw angles each, then we've got 25 simulations. So that's where it starts to get this exponential growth. And design of experiments is important once you get into this part of things. But we're just trying to simplify it right now for the end user.
Okay. And then one of the things that we've noticed with testing over the years is that shockingly small changes make relatively large differences in your results inside the tunnel. And it's been hard for us to do that or see that numerically. So I'm wondering if with a highly detailed scan, are you able to pick up things like really minor things like the tire tread patterns and see if there are any differences between one tire and another, or small differences like
a difference in PSI. So as you change the PSI of a tire, its shape changes. So even we've seen that 5 PSI can make a relatively large change in aerodynamic drag. Is your system accurate enough to pick things like that up?
So the short and simple answer is no, which is not a very good marketing answer.
No, it's honest though.
Yeah, but I'm not going to try and pretend that we can capture things like that. What we're focused on is if you break it down, like 80% of the drag more or less comes from the rider and about 20% from the components.
Okay.
And while things like wheels, I think, have the largest impact on drag as far as components go, you're still dwarfed by the contribution of the rider, especially if you're wearing like a flappy jersey or we actually had someone get scanned wearing a t-shirt once, which I was kind of wondering, like, why bother? But anyway, that's besides the point. But what we're trying to capture is the large changes, and you can capture some of these things numerically, but even at the best, like fabric textures, they take supercomputers to really get the details, and that's for a very, very small model. Like small in terms of the physical size of that model. So it's not really practical from a numerical standpoint, but this is also why I advocate using multiple methods, because now you can go through and you can test these things with the wind tunnel, and you can modify your position, optimize that, and then you're minimizing the number of variables you actually have to look at when you go to the wind tunnel. Picturing
somebody scanning themselves in a t-shirt is making my day.
You would be surprised sometimes.
You got the engineer in the room going, "Gosh, what is happening here? How is this even possible?" Oh, that's great. Okay, so that's really cool. And we've written articles in the past on people really obsess. We call them, large scale changes and small scale changes. And I always like the one example I give when it comes to wheels is the large magnitude change, if you will, happens when you go from a stock aluminum training wheel to any race wheel. I don't care if it's us or Envy or Zip or Reynolds or whoever. You're getting, 95% of your gain there. And then when you start to compare things like, the difference between Zip and FLO or Envy, or the difference between a front 60 or a front 80 or whatever the depth is, now you're really getting into these very small differences, and you're looking at, 1 to 5% of an improvement, but you've already gotten the 95+% improvement from just the first switch. So I think what you're saying makes a ton of sense, because if your software was picking up the difference of 5 PSI on a tire, it's maybe too detailed, but because the rider is 80% of the drag, you're really helping the athlete pick up the lion's share of what they need to focus on. And that's really effective for, in my opinion, 99% of the people who are likely using your software.
Yeah, and that's exactly what we try to go after. We're not trying to literally reinvent the wheel or anything. Yeah. But it's just these large scale changes that make the most difference. And based on your experience, if you were to test, like I know you test your wheels in isolation just because that minimizes the number of variables, and it also allows you to get a cleaner signal that's proportionate, or at least you can scale the measurement proportionate to the drag. That. Yep. If you're measuring 20 or 30 newtons of drag at a certain speed for an entire rider versus 1 to 1.5 newtons, the experimental error becomes so much larger with the full rider. So even if there is a difference, having different tires, something like that, it kind of gets lost in the noise for the full scale test.
100%. And that's like, we've taken a lot of heat over the years for never using frames or never using riders or all of these different things. And I get the argument. Like, it does make sense because the entire system is what an athlete uses. But there are, we've talked about this before, but there are studies that people do, you'll get like a crowdsourced study, right?
Oh, yeah.
They go into the wind tunnel and they do a study, and people use it as gospel. It's like, oh, well, that bike is the fastest. But if you look at their protocol, I remember I looked at a protocol of one, and I found 300 grams of drag of error just in the way they set their tires up, right? And not saying that those studies are useless. That's not the point. But
the more variables that you add to the equation, the harder it is to get an accurate look at what you're comparing. Because one bike to the other, like, is the derailleur cable longer on one bike versus the other, the rear derailleur loop? Mm-hmm. That's going to have an effect. And I know that sounds crazy, but we've picked up differences in the exact same tire, but if the manufacturer uses 5 molds, one mold of the exact same tire will be faster than the other 4, right? So if you can pick that up, and it's not just us finding that, it's like all the manufacturers finding that, to put a rider on a bike and say that he can hold a position as accurate as like the differences between mold variations, is like, it's impossible to say that like one bike is better. So that's kind of been our big push on this, focus on the large magnitude changes. Like if you're showing up to Ironman and you're using gator skins, well, you lost, right? But like, so just use what makes sense. And I like your system, because to me, what it's showing you is it's like, hey, we're going to give you the 95% of what you got to focus on. And the rest of it, if you want to be obsessive and like lose sleep over it, you can, but you're probably not going to save that much time. So that's really cool how that works for you guys.
Yeah. And honestly, we put the onus, well, maybe not onus, but the responsibility on other people to provide test data. And you guys are super transparent, which I love. Other manufacturers, not so much, where they just say, hey, we're faster, and then just accept it. But yeah, like having those changes in equipment, yeah, it'll add up a little bit. But you kind of have to take people at their word for that. Like not everyone's going to go to a wind tunnel and validate all the results. And yep. Like you were saying, experimental method is a huge part of it. And knowing whether or not, the proper performance is achieved and even the proper experimental procedures followed. That's a huge part of it, because manufacturers will always cherry pick data that makes them look good. Like, why would you publish something that makes you look terrible?
Right. And we've learned that because for the first time we ever went to a wind tunnel, we had no idea that tires could have this massive effect on your drag. And I remember the first set of aero data that we published, our 90 was slower than our 60. And we just told everyone that it was slower because that's what the data said, right? And it made us look bad. Like we actually published data that made our design look horrible. And people were like, who would ever do that? And we're like, well, I guess we're honest. But, over the years, we've learned that if you get the tire from the right mold, mm-hmm. your wheels look faster than a competitor. And if a competitor doesn't know that, it could have an effect, right? So this is the thing, like again, I'm on a rant here and I'm going to end it. But my point is, it's just like, be careful. Like just know that most of the obvious things that you need to focus on are the big scale things, and the small stuff is kind of small, is almost pointless.
And kind of touching on that rant there, there's a good engineering humor saying that I've heard where it's, see if I get this right. No one believes numerical results except the person who does it, and everyone believes experimental results except the person who does it. So I think that holds true.
Very good. All right, my rant's over. John, go ahead.
Yeah. So we talked a little bit earlier about scanner technology and those sorts of things. Let's say that you could pick the most accurate scanner that you could get your hands on. Right now, you're within 2% accurate of a wind tunnel, which is pretty amazing. If you had the best scanner available, do you think you could reduce that amount of that 2% accuracy? Do you think you could take it down even lower?
I would honestly say not significantly, because each time you get on the bike, you're getting on slightly differently. And that's going to be a larger source of uncertainty than the actual scan error at this point. There are a few things that could be improved, but in general, that would kind of be the way I lean on that answer.
I think what's really interesting is it's really cool to know that today in your hand, in a cell phone, you essentially have enough scanning technology to produce the results that you are. I mean, this has been a fascinating podcast, but just to understand that an iPhone today can essentially, I mean, if you would have told us this 10 years ago, I mean, we thought the CFD we were using back then was crazy, but to even get a scan like that is it's fascinating. I mean, that's the complexity that goes into the scanning, and for those of people that are listening that understand, meshing, and if you don't understand meshing in computational fluid dynamics, like you're saying earlier, the millions and millions of cells and the computation power that goes into that is it's unbelievable. And I mean, that's essentially in the power of your hand now. It's crazy. It's really cool.
Yeah. So think of that next time you're watching a cat video on YouTube. You're using a supercomputer to laugh at cats.
Yeah.
Yeah, exactly. You really are.
Awesome. So this is the question that most guests cringe over. It's our famous Watt Point question, but you're like super genius engineer, dude. So you're probably like excited for this question.
I love numbers.
Yeah. The idea behind this question is if the listener follows the advice or uses the service, whatever, of the guest that we had on the show, how many watts does that add to their FTP? Or how many watts does that save them in this case? So we always use a rider with a 300 watt FTP, but in this case, the FTP isn't really important because we're just looking at a reduction. So if you take, with your software, how many watts have you been able to save people in the past? Like a guy sends in a position, a relatively bad position, you make some modifications. How many watts are you saving people?
I would say in the extreme case, 50 watts is not unreasonable.
Wow.
More often it's like 20. But that's a pretty common result. Sometimes it's less. Some people are pretty optimized already, and that's just through trial and error. But there are some people that have really terrible positions. And it is just unbelievable how much a change in position, which costs you virtually nothing, can save you in terms of performance.
Was T-shirt guy the 50 watt case?
I think he may have exceeded that. I
100 watts.
Yeah. That one would have been pretty substantial.
Yeah, no kidding. So 20 watts is a lot. I mean, considering the average guy's FTP is probably what, 240, 250, I'm guessing. I mean, that's 10% or just shy of it, right?
It's pretty significant, but the caveat there is with aerodynamics, your power goes up, or the power requirements go up with the cube of speed. So you hit a wall pretty quickly. So even though it's 20 watts, like that 20 watt savings, it's not like adding more power to the equation. You're just, by going faster, you're like the V squared term, it's actually V cubed in terms of power. That just grows so quickly that it is a little bit maybe disappointing to see how much or how little of a difference sometimes it can make, but it's still 20 watts that the guy beside you might not have, or the girl beside you.
I've got a few more questions now that you said that. I want to ask a couple things. So you're sending back fit data, right? You're sending back new fit information for a rider. It's like change your pad stack or reach X amount.
Mm-hmm.
How are you making sure that positional change isn't going to injure the rider or it's a safe position for them to be in?
So that's a very good question. I try not to comment specifically on bike fit because I'm not a fitter and I don't want to be encouraging people specifically to make changes. And a lot of our partners
just get them all laid out, super sleek. A
lot of broken riders after.
Yeah.
But a lot of our partners are fitters themselves, so they're filtering the data, or they're at least able to provide recommendations. But what I always encourage people is, well, first of all, I try and get an idea of how flexible someone is. Like, do they feel like it would be reasonable to make certain changes? And I always encourage people, give yourself a month, 2 months, 3 months to adapt to a change before racing in that position. Okay. And then it just gives your body time to adapt, because you can't make an overnight change, even if it's relatively small. It still could potentially hurt you. So I always tell people, take it easy. It's better to finish the race or to stay in aero position than it is to have a slightly more aerodynamic aero position that you can't maintain for more than 5 minutes.
Yeah, and the reason I asked that is because we've had Jim Anton was on the show. He's a fitter. Mm-hmm. And your position can actually affect your power output by quite a bit too. So there's always that trade-off. You could maybe get in a more aerodynamic position, but if you're closing your lungs off and you can't breathe effectively, or who knows, maybe you just aren't able to generate enough power, that also goes into the equation. So it's cool that you're working with fitters, because they can kind of be the filter on the other side to make sure that what they're doing is actually not going to affect the power output that the athlete can produce.
And actually, touching on that, your power can definitely be affected. And there's kind of a trade-off where you get more aerodynamic, you get less powerful. But there's a paper that recently came to my attention that you actually generate more heat in different conditions or in different positions. So your metabolic cost is higher, which means if you're marginal for being able to stay cool at a race, being in a more aggressive position might actually be worse for you, because you might be generating 200 watts of the pedals, but you're now dissipating 900 watts instead of 700 watts.
Whoa. Okay, wait. You have a link to that study?
I will pass it along to you, but it's I'll see what I can do to dig it up.
So, in a nutshell, are you able to say what causes an athlete to not be able to dissipate more heat? Is it just that there's less airflow around their core, or what is it that's causing that?
Well, the dissipation's one thing, but the actual generation, and this is so. If this is getting off onto another tangent, and to be honest, my biggest interest in athletics is heat generation and heat dissipation. So the aerodynamics is one thing, but like my PhD research is actually focused on heat transfer, and this is what I love dealing with athletes, is figuring out, okay, how do you keep someone cool? So there are significant changes that can be made to affect more cooling on a specific athlete. And there's simple changes too, like the amount of energy solar radiation that you're basically absorbing. If you have a black matte jersey versus like a reflective white jersey, that can be like an extra 100 to 200 watts of heat that your body has to dissipate. And then the evaporation difference in a place like Kona versus a place like Arizona is very significant as well.
Okay, you maybe just sparked another podcast, so we may have to talk about that at a future day. Okay, my last question: I'm guessing you're getting primarily triathletes. Are you getting road cyclists as well doing this, and mountain bikers and gravel guys, or what?
Primarily, it's been triathletes.
Okay.
We have started to see an increase in the number of road cyclists, and we've got a partner in Norway who's very well connected. And he's been working with a lot of the continental and pro riders in Norway. And I think the argument there, a lot of people say, well, you're always in a peloton, but what about the guys who are doing a breakaway? Or what about the guys who are towing out a rider before a sprint? Like, you need to optimize your aerodynamics for those guys. It's not necessarily like the Peter Sagans or the Chris Froomes that would benefit as much, but it's the guy towing them out, the
who sits on the front for 3 hours,
who gets no credit and does all the work. Well, not all the work, but so those guys are the ones that really should be optimized, and I think there's such an opportunity that's being missed in terms of optimizing those riders, because if you're sending someone on a breakaway, like, you want them to be able to, in a lot of cases, you want them to be able to stay away. So I think there's, a lot of people are going to start to realize this over the next year or two. And we have had some interest from some of the pro teams in applying the technology to looking at packs of riders drafting and how to optimize that. So there's tons of different applications. Like, we're only scratching the surface here.
Oh yeah, that's wicked. You could basically optimize the peloton shape for aerodynamics.
Yep. There's and you see kind of the self-selection or self-optimization where you get echelons forming in crosswinds, and that's really
It's interesting you say that. Have you seen? Did you see the guy who broke? I forget his name. He broke the, or he ran the marathon under 2 hours. It was a thing that was put on, but one of the ways that they did it was they had a car out front, and the car that was out front had an array of like lasers that shot specific patterns on the ground. And so those patterns were for the guys that were out front. So they basically created a V. So their job was to stay on that pattern. And then the runner had a spot in the back. And so he was in like white. The other guys were in black. I mean, it had to do with like heat. It had to do with a whole number of different things. So that aerodynamic setup for a guy running like essentially 13.1 miles per hour was critical. So if you think about adapting that to something like a tour, like if they could learn to ride in formation, I mean, it could be monumental.
Absolutely. Yeah. There was a lot of research that went into that. And there was a bunch of CFD models that they used to predict the optimum shape. And I think what they ended up with was something that was kind of counterintuitive. It was like almost a reverse V or a diamond that they ended up at least testing at one point and found it was quite effective. And no one had predicted that.
So the birds have got it all wrong then.
Yeah. Yeah, take that, evolution.
Yeah. All right, man. This has been an awesome show. Very interesting guy. Every time we talk, there's always something cool coming up. How can people learn more about your virtual wind tunnel, what you guys are doing at Four Eyes, all that?
So the virtual wind tunnel, I think we're just transitioning over from our old stackzero.com website, but it was previously under stackzero.com/VWT. It should be under 4eyes.com. So that's the number 4 followed by I.com. And then I think there's possibly /VWT there. I should have been more prepared with this. But you can also reach out to us directly. If you send an email to our general info address, then we can definitely get in touch with anyone who's interested in either becoming a partner or having themselves scanned.
Okay. Awesome, man. Well, thank you so much for coming on the show. It's been an excellent episode, and we will see you soon.
Thanks a lot.
All right, man. Take care.
Hey, this is Chris with FLO. When we're not producing this podcast, our team at FLO is designing some of the fastest carbon fiber bicycle wheels in the world. As a thank you for being a listener of our podcast, Faster by FLO, we wanted to offer you 20% off your next purchase of wheels at flowcycling.com. Head over to our website and pick up a set of wheels to make you faster at your next race or ride. Simply use coupon code PODCAST. That's PODCAST in all uppercase letters when checking out to get 20% off your order. Thanks again for listening to Faster. We hope you enjoy the show. Thank you for listening to this episode. Be sure to listen to episode 36, where we interview clinical and holistic nutritionist Krista Orecchio to discuss your gut microbiome. During this episode, we'll learn how a healthy gut microbiome can improve your health, which in turn will help you become a faster cyclist. If you enjoyed the show, please help us by sharing our podcast and by leaving a rating or review. If you want to learn more about our company, FLO Cycling, please visit us online at flowcycling.com. That's F as in Frank, LOCYCLING.com. You can also find us under FLO Cycling on Facebook and Instagram. Until next time, ride safe.